Hello everyone, this is lecture 8 of course PE 645. In today's lecture we are going to deal with a new type of features called shape features. Shape features are critical components in image analysis and computer visions, especially when we are working with region of interest or ROIs. As you saw in our previous lectures, we were dealing with a specific ROI by applying masking on the original image and extracting this ROI and then applying grouping to them to avoid any surrounding black pixels. Shape features help in characterizing the geometry of objects, which can be useful in various applications such as object detection and recognition, medical imaging, and pattern classification. So you can simply apply a classifier based only the shape features and the geometry of the objects. For medical image analysis, shape features are essential as they provide critical information about the anatomical structure, pathological changes, and other relevant entities within the images. For example, if we are going to classify a tumor, we can include the geometry of the tumor in our features, such as size, area, and other features as we are going to see. These features will help to differentiate between normal and abnormal tissues, classify diseases, and even guide treatment decisions. In this lecture, we will split the 2D features and 3D features into two parts because the features in 2D will be different from the corresponding in 3D. For example, the area in 2D will be surface area in 3D. So you will notice that the 3D features that we are going to apply will be in somehow different from the 2D features that we will use. So let's begin with the 2D features. There are many 2D features, not only the presented in this lecture, that can be utilized in your classifier and set of features. Some of them are the area, and the area is the total number of pixels in the ROI, and if we are reflecting that on a tumor or a scan, we can say that large areas may indicate larger structures or lesions within the ROI. The perimeter, and this is the total length of the boundary of the ROI, the centroid, which can be split into the centroid in X and centroid in Y, because we are dealing only with the width and height. And this is the geometric center of the ROI, the bounding box. The bounding box is the smallest region that can include the ROI, and we have dealt already with the bounding box during capturing the box that surrounds the ROI. So based on that, we could remove the surrounding black pixels. Aspect ratio, and this is the ratio between the width and height of the bounding box. Compactness, and this is a measure of how closely packed the shape is, and higher values of the compactness will indicate more compact shapes, potentially indicating malignancy if you are dealing with a cancer. Eccentricity, this is a measure of indicating if the shape goes to be a circle-like or indicates some sort of elongation. So the value of eccentricity will be between 0 and 1. Values closer to 0 will indicate more circular shapes, while values closer to 1 will indicate elongation. Convex hull, and this is the area of the smallest convex shape that can include the ROI. Extent, this is the ratio of the area of the ROI to the area of its surrounding bounding box. So values close to 1 indicate that the ROI fills the corresponding bounding box, because the area will equal to the bounding box area. And smaller values of the extent will indicate irregular shapes, because in that case the bounding box will be larger than the area. Solidity, this is the ratio of the area of the ROI to the area of its convex hull, and higher values, which means that the numerator that reflects the area is higher as a value, and this will indicate more solid shapes. And major axis length and minor axis length, they reflect the major and minor axis of an ellipse. So if we are drawing an ellipse around the ROI, or if the ROI is close to be an ellipse, So the major axis and the minor axis will be something like that. Orientation, this is the angle between the major axis of the ellipse and the x-axis, and mu here and here reflect something called central moments. And the central moment will help quantify the spatial distribution of intensity within the ROI. So simply, if we substitute P by 0 and Q by 2, we will get that value of mu. And if this value is 2 and this value is 0, we will get the first value. And last but not least, the roundness. And this is a measure of how closely the shape resembles a perfect circle. And also, if the value is closer to 1, this will indicate circular shapes. So if you applied these features and any other shape features to a specific dataset that contains multiple regions or multiple ROIs, we can concatenate all features together as we did in the machine learning classification lecture. And based on the shape features, we can train the classifier to obtain the decision. So for example, if we have an image that consists of multiple ROIs, as we saw during extracting the features from the left lung and the right lung, we can obtain the shape features for that ROI and that one and that one. And now we have two options. If all of the dataset contains 3 ROIs, which is not a usual case, we can set the features to be split into 3 regions. The first region will be for the first ROI, the second for the second ROI, and the third for the third ROI, and finally we add the class here, so we get a file that we apply to the classification process. And the other approach, which is usual in many applications, that some images will contain 3 and others contain 4, and the whole dataset will contain varied numbers of ROIs, and in that case you can compute the features for each ROI and then average the results into a single set of features. So in this case, we will add here the average values of the corresponding features that reflect the ROIs. And finally, we add the class here. So depending on the application, you can, in that case, optimize the classification file that will be applied to the classification process. Another example, and in that case, we can obtain a dataset that internally got multiple ROIs as mentioned, but each ROI will reflect a specific category or a class. For example, this one is normal, this is benign, and this is malignant. So in a single case or in a single image, we have multiple categories. In that case, we will treat each of them individually. How to do that? Simply, we have dealt with adding a set of features per image, but in this case, we will add a set of features per ROI. So in our classification file, we will get the shape features of the first ROI and add it in our file and add the class here to be normal, and then add another record for the benign here and a third record for the malignant here. So in that case, instead of horizontal expansion, you will apply vertical expansion. So you apply horizontal expansion by adding the features for each ROI together if they reflect the same category. But if they are not reflecting the same category, you are expanding vertically. And in this case, you cannot apply the averaging, because if you did that, you will mix between the 3 classes together, and imagine if you did that by mistake, which class are you going to put here? Normal, benign, or malignant? So this approach for multiple categories will be a mistake. So how to apply the process of extracting the shape features from the cropped version? First, we have imported the packages and then extracted the ROI as we did, and then cropped the ROI to remove the surrounding black pixels. Then we started to calculate a feature by a feature. First, we calculated the area by counting the non-zeros from the cropped version. And here we are ignoring the zeros and counting only the non-zeros areas from 1 to 255. Then we calculated the perimeter by getting the contour that surrounds the cropped image, and then got the largest contour, and based on it calculated the arc length of it. For the centroid, there is a function called moments that will get and implement the moments function internally, and we can access the moments by adding the PQ, P and Q values here. So if you need the P to be 1, Q and to be 0, we write moment 1, 0. So to calculate the centroid X, we divide the moment of 1, 0 by moment 0, 0. And the centroid of Y, we divide the moment of 0, 1 by the moment 0, 0. After that, we calculated the bounding box using the bounding rect function that we used it here, and this function returns x, y, width and height of the rectangle that surrounds the object. Then the aspect ratio will be the width divided by the height, and the compactness we apply the formula, and eccentricity is the same, square of 1 minus the moment of 0, 2 divided by the moment of 2, 0. Then calculated the convex hull using the convex hull function provided in the OpenCV, and to calculate the area we took the convex hull, applied it to the contour area to calculate the corresponding convex hull area. And the same we did with other formulas such as solidity, major axis length, minor axis length, orientation, and roundness. And finally, we printed all of these features. If we executed the code, these are the following results. So we can get these results and append it to our file to be used in the classification process. For example, the aspect ratio is 1.58 or approximately 1.6, which implies an elongated shape compared to a perfect square, and the compactness here is 1.89, and this means that the ROI appears to be densely packed. The eccentricity is 0.77, and this means in somehow it can be moderately elongated or reflect an irregular shape. So if you draw a polygon like that, this means that it's elongated. But if the result was close to 1, this means that that value and that value will be approximately similar, which will reflect something like a circle. So in this case, the shape is not perfectly circular. The extent is 0.56, which means that the ROI occupies approximately 56% of the surrounding bounding box. So this shape, and this is the bounding box, so this shape fills only 56% of this bounding box. And this is true because we have large region here and large region here that's not included to the ROI. And the orientation angle here is negative 0.45, which indicates that the major axis compared to the x-axis got an angle here is about 0.45, and the negative means it's counterclockwise. And finally, the roundness here confirms that the shape is not a perfect circle. Now we need to move to calculate the shape features for a 3D volume. We will do the same process to read the volume by getting the images and the corresponding masks, apply the extraction of ROIs and combine them together, and then pad the volume or the images, then combine them to unify the shapes. There are many 3D shape features. Some of them are covered here, such as the volume, and the volume will measure the total number of pixels or cells or elements inside the shape. Surface area, and this is the total surface area of the 3D object. Surface to volume ratio, and this is the division of the area to the volume. Sphericity, this is a measure of how close the shape is aligned to be a perfect sphere. Higher values will indicate more spherical shapes. Compactness, similar to the 2D, it's a measure of how compact the shape is relative to its surface area, or a measure of how dense and compact the shape is. Convex hull is the total surface area of the convex hull of the shape. Convexity, it's a ratio of the shape's surface area to its convex hull area. So we are calculating the area and dividing it by the area of the convex hull. And this is a measure to indicate how much the shape deviates from being a convex. Euler number, which is a topological property which is related to the connectivity and structure of a 3D shape, and it's useful to characterize the connectivity and holes within the shape. Elongation and flatness, they are based on calculating Lmax, min, and intermediate, and they reflect the longest dimension, the minimum or shortest dimension, and the intermediate dimension between them. So the volume will have 3 dimensions. The maximum of them will be called Lmax. So for example, this is 3, this is 5, this is 1. So Lmax here will be 5, and Lmin will be the minimum of the dimension, which is 1, and the intermediate will be the one between the minimum and the maximum, and in this case will be 3. And elongation is a measure of the degree of elongation or stretching of the shape. As mentioned in the 2D features, we have something like a polygon, and if the major axis is higher than the minor axis, this means that there is an elongation and a deviation from being a perfect circle. Flatness, this indicates how flat or planar the shape is along its smallest dimension. Rectangularity, this is a ratio of the volume of the shape to the volume of the bounding box, and this is a measure of how closely the shape fits the bounding box, which we calculated in the 2D features to be the extent. And last but not least, spherical disproportion. It's a measure of how much the shape deviates from being a perfect sphere. So you will notice that the descriptions between the 2D feature and the 3D features are close together, but the names are different. Let's move to the code. To calculate the 3D features, we have 2 options. The first option is to implement it manually, and in this case it will be difficult because calculating many of these features will require us to build something called a mesh. And a mesh has different definitions, but commonly it reflects the surface and interior structure of the shape by applying a 3D object representation that consists of a collection of vertices and polygons. And to apply that manually, it will take time to process a single image or a single volume, as there are many algorithms. Some of them are fast and others are slow. So instead of doing that, we can deal with another approach, which is using a library that implements that internally. One of these libraries called TryMesh. So TryMesh is a package that facilitates for you the dealing with the polygons and meshes, and also this library provides many features that can be used. So to use the TryMesh, you need to install it using the pip command pip install TryMesh and then import it. And here we implemented a function called shapeFeature3D that accepts the volume, and that volume is later passed to the function from the readVolume function that we implemented earlier. And after a while, I will illustrate the meaning of these lines. So let's move to the shapeFeature3D function. To convert the volume or the matrix into a mesh, we can use a function called matrix to marching cubes, which is available in the ops voxel TryMesh module. So this will return the corresponding representation or the corresponding mesh representation that we can use it to calculate the different features. So we calculated the volume, which is the sum of that volume, and the sum here will automatically ignore the zeros because the summation of zeros is 0. Then calculate the surface area from the mesh object using the property area, then surface to volume ratio and compactness and sphericity. Then we calculated the bounding box using the property bounds from bounding box from the mesh object. Then we calculated the elongation and flatness. After that, we calculated the rectangularity and spherical disproportion, and finally the Euler number, which also can be accessed from the mesh using the property Euler number. Then we returned a dictionary that included all of these features. After that, we printed the shape features to be displayed on the command window. So what is that? Here, instead of only dealing with 3 elements that we dealt with in the previous lecture, we here imported all of the images that have a corresponding mask. So here we have the volume and segmentation slices. We can open the segmentation slices to get the index or the number and scroll down until you reach to a mask with a white region, and here you find 45, and then you scroll down until the end. You find the end of the masks is 73. So we need to capture the shape features for these images. So instead of writing 29 lines for the masks and 29 lines for the files, we simply made a for loop that will loop from an index to another index, and that index will be added here. And to do that format, don't forget to write here f that reflects format. So for each of them, it will get the corresponding index and fill it here. And finally, this list will be occupied by the 29 elements or the file names. So the starting index will be 45 and the ending is 73, as we mentioned here, 45 to 73. And this number varies from a case to a case. And here we added 1 because the range is not inclusive. This means that the last number is not included, so it will end here by 73. Now we have the files for the masks and the images. We passed them to the read volume, then we got the features. Also, you have an option to display the mesh representation visually by simply using the same statement here and function matrix to marching cubes to get the mesh. Then you get the scene of the corresponding mesh, and then use the function show and define the resolution, which is width and height of the window that will appear to you. When you execute the code, it will display the corresponding feature as shown, and it will also display the scene that reflects the mesh. So it's something like that, and you can navigate to that 3D by keeping the left clicking and navigating to the object. And also you can zoom in and zoom out using the wheel. Something like that, as that, like that. So the more slices with you, the more the height it will appear. Because only we got 29, it showed only 29 slices here. This is the width and the height, and this is the depth. As you see, this is the 3D volume of the corresponding mesh. So if you zoomed in, you will find that the mesh consists of boxes, as you see here. This is a box, this is a box, this is another box. So the function role here is mapping and filling the 3D volume with boxes. So in this lecture, we have dealt with a set of shape features that can be calculated for the 2D and 3D volumes. And as noted, there is some differences between the 2D and 3D features in the names and formulas, because here we are dealing with only width and height in the 2D image, and in the 3D volume we are dealing with width and height and depth. And for the 3D volume, we dealt with a library called try-mesh that will convert any volume or any 3D matrix to a corresponding mesh. And this library also provides a set of features that can be accessed, as we saw. And finally, we saw how to visualize the mesh by converting the mesh to a scene, and that scene will be displayed using the show function.